Welcome to today's deep dive. We are unpacking a really fascinating stack of sources for you today.
Yeah, definitely.
We're looking at a technical presentation on precision transmission vocabulary. So our mission right now is to decode the exact language that mechanical engineers use to, manipulate metal. We're talking about turning raw steel into indestructible gears.
It is, it's an intense world for sure, because we tend to view heavy machinery like jet engines or transmissions as just solid and immutable right out of the gate.
Right, like it was just born that way.
Exactly. But steel doesn't start out that way at all. To handle extreme stress, the material actually goes through this highly orchestrated thermal choreography.
And looking at the sources, the first step in that choreography is actually pretty surprising.
Yeah.
Because before you can harden the metal to survive stress, you actually have to soften it.
Yeah, that's the process of annealing. So engineers will take something like a forged gear blank, which, already has a lot of internal tension just from being stamped or pressed into shape.
Oh, right, because forcing metal into a shape stresses it out.
Precisely. So they put it through a slow cooling heat treatment, and this relieves that residual stress and drastically improves its machinability, so it cuts consistently.
Okay, let's unpack this. If I'm picturing it, annealing is essentially giving the metal a warm massage.
Right.
Like you have to completely relax the structure before you can safely machine it.
At the molecular level, yeah, that is exactly what's happening. The heat allows the atomic structure to just relax. But then once you've cut the gear, it obviously needs to survive real-world high-load friction.
Right, so it can't stay soft.
No, not at all. So then the metal goes through quenching. You rapidly cool the hot steel, usually using a high-speed quenching oil.
Which is basically like taking that perfectly relaxed metal and just throwing it straight into an ice bath.
Yes, exactly. That sudden temperature drop forces the molecular structure into a state called martensite. The atomic structure literally gets trapped because the cooling is so rapid.
So the atoms just freeze in place.
Pretty much. The carbon atoms don't have time to diffuse out of the crystal lattice, so they get stuck. And that stretches the lattice into a state of permanent high tension. That tension is actually what gives martensite its extreme hardness.
Wow. And I saw they use specialized quenching oils for that to minimize distortion, especially in thin-walled components.
Right, because if you cool it too violently or unevenly, thin parts will just warp.
Okay, wait, I need to push back here for a second.
Yeah.
We just rapidly froze the metal to trap the atoms and make it incredibly hard. But the next term in the presentation is tempering,
Yeah.
which means reheating the quenched metal. So doesn't applying heat just, undo all the hard work and that violent atomic tension we just created with the ice bath?
You would think so, yeah.
A little
But
bit.
you really have to consider the physical reality of martensite. Extreme hardness brings extreme brittleness.
Oh, like a diamond.
Exactly like a diamond. It's incredibly hard, but if you hit it with a hammer, it shatters into a million pieces. If you put a freshly quenched, fully martensitic gear into a transmission, the teeth would literally just snap right off under the first major impact.
I see. So tempering is the critical compromise here. By reheating the metal, you give those trapped atoms just enough energy to relax slightly without losing everything.
Right. You aren't melting it, you are just providing enough thermal energy to relieve a fraction of that internal stress. This thermal push and pull is the only way to synthesize contradictory traits.
Strength and flexibility, you mean?
Yes, you get maximum strength and necessary flexibility within the exact same piece of steel. It prevents brittle fractures while retaining the hardness you absolutely need.
But looking at the physics of something like a planetary gear under extreme torque, sometimes tempering still isn't quite enough of a compromise, right? Because it needs intense surface hardness for friction,
Yeah.
but a highly flexible core so it doesn't crack.
Yeah, you can't always achieve both of those things evenly throughout the entire piece of metal. Which brings us to surface manipulation.
Case hardening.
Exactly. When a single component needs completely different properties on the outside versus the inside, engineers use case hardening. It creates a hyper-hard shell for wear resistance while leaving the core really tough and flexible.
And the sources go even further with something called induction hardening, which I found super interesting because it's highly localized. It's not just treating the whole surface.
Induction hardening is fascinating just because of the mechanism itself. Engineers use an electromagnetic coil to generate an alternating magnetic field around a very specific spot, like, say, just the shaft journals.
And that invisible field induces an electrical current inside the steel, right?
Yep. And because steel naturally resists electricity, that resistance generates intense, rapid heat in just that exact millimeter of metal. Then they immediately quench that highly specific area.
While the core of the shaft remains completely unaffected. That is wild. You are essentially using electromagnetism to give a single piece of steel a dual personality.
That's a great way to put it. It really is like giving the metal a dual personality.
So to bring this all together for you listening, mechanical engineering isn't just about cutting and bolting metal together. It is about fundamentally manipulating time, temperature, and invisible electromagnetic fields.
Yeah, you're completely rewriting the physical limits of material. We tend to assume the objects around us have fixed, static properties, but they don't.
Right, those properties are the result of intense microscopic engineering. Which leaves you with this to consider today. Knowing that engineers can completely alter the identity of steel just by changing its temperature, look around at the everyday objects in your life.
Yeah, it really makes you think.
What hidden, extreme structural capabilities might they be hiding just beneath those seemingly static surfaces? Thanks for joining us on this deep dive.